In this video lecture I will discuss the inference method of the Desparsified lasso. So like the post-double selection method, we're again using a free-swap kind of argument, but in a slightly different way. Here, for this method, we start from the first order conditions of the lasso. So take the lasso, standard form, and remember what we showed in the earlier lectures was we had this first order condition where this Sj was this subdifferential either equal to 1 or minus 1 if beta j hat was not 0, or some value in between the interval minus 1 and 1 for a beta j equal to 0. Well, we can of course also write that in vector form. So we put all the first order conditions for j is 1 to be together, and then we get these first order conditions where I just move some stuff to the other side. Now, let's do some different notation, and let's write x prime x over n as sigma hat x. And we can use this actually as an estimator, of course, of the covariance matrix of the x's. And write sigma hat x beta hat, which comes from the previous slide here, and plug in for y the true expression for y. And then we can rewrite, because we again get x prime x over n, so again sigma hat x times beta, so put that to the other side, and we end up with this expression here. Now, if you could take an inverse of this thing, well then you can just pre-multiply with the inverse. You get something beta hat minus beta, and you get something here which looks good because x prime epsilon will give you normality. So, but of course we can't, given that this is high dimensional, it will not work. But let's assume we can find an approximate inverse, call that thing theta hat x, such that if you pre-multiply sigma hat x with theta hat x, you get something close to the identity matrix, but not exact. And in fact, we don't want it to be exact. And then what we can do is, if we pre-multiply that with that thing, well, you can then say, okay, well, it's going to be approximately beta hat minus beta, but not entirely. So split beta hat minus beta and add the error that you make in your approximation, and then move this to the other side. So we want to get rid of that. So we have beta hat minus beta alone here. We get x prime epsilon times this approximate inverse. We get the subdifferential term, and we get, I'm going to call this delta now, the error that you make with this inverse approximation. Now, what we want to hope is that it's small enough such that actually the largest entry of the vector is going to converge to 0 probability, and because of course in that case, well, we can basically ignore that part. So let's rewrite a bit further and get the s part, because that is still the one that is going to be a tiny bit problematic. Let's move that over to the other side. So because this is what we want to have, right? I mean, this is the part that you would normally only have when you do look at least squares, for instance. So that's the part you want to have. This gives you a nice normality in a uniform way, because there's no beta in there. So we move this part to the other side, and then we're going to reuse the first order condition, because we can write this s times lambda over 2. It's just x prime y over n minus x prime x beta hat over n. Well, if we do that, if we plug that in, and in particular, if we then put terms together, this beta hat and theta x times x prime y minus x prime x beta hat, so it's all these terms, then we call this thing the Desparsified lasso estimator. So we start with the lasso, and then we add something to it. Now, the reason why we add that thing to it is because now we have this nice term on the right hand side. Well, and this term will give us normality exactly as we want to have. So what we're doing is we're adding essentially some noisy correction. So we're killing off the zeros because this, of course, will not be 0. And we're killing off the zeros in the beta hat. And by doing so, we eliminate model selection. And that actually is enough to make convergence uniform. So you sacrifice zeros, but in turn, what you get instead for that is something which has actually a normal distribution. It has so in a uniformly valid way. And we can also easily construct standard errors because we can just use this sandwich form here. We don't even need to write out what the probability limit of that thing is. I mean, the most important part is that we have this, because this is something you can just calculate. So if you want to do testing or something, you can just use this standard error. Now, of course, the crucial part is how do we get this theta hat x, like this almost an inverse thing. Well, for that, and here comes the Frisch-Walk argument again, what we're going to do is we're going to regress every column of x, so every variable, say xj, on all the other variables. We can call that x minus j. And we're going to do that, of course, then using the lasso, because this is still high dimensional. And then we let gamma hat j be our estimator for applying the lasso for xj on all the other variables. And if we collect all those gamma hats and we put them in rows of our matrix, then we're going to work towards this theta. So for the first row, we're going to put a 1 because then we're actually regressing x1 on the others. And we'll do x1, and then here we put minus the coefficients there. Well, for the same idea for x2, we put a 1 here and we put all the other coefficients in that row, and so on to the final regression of the last variable on all the others. Why does this work? Well, let's have a look at what we would do if we multiplied the sigma hat x matrix with, now say, the first row of our gamma hat matrix. So we get 1 and then minus the coefficients. So that will give us x1 minus gamma hat 1, x minus 1. So in fact, what we get here are residuals. So we get a transposed form actually of the residuals of the Lasso regression of x1 on all the other variables. Well, we can of course then write it out further because we can multiply it with this. So we actually get x1 prime x1 minus this part, and for the latter part we get this part here. Now, to have an idea of why this works, assume that actually you did not do Lasso, but you could do least squares. Well, then you can write out these things. You can write out these expressions. And if you do so, what you'll find is that essentially what we're getting here is, in the first entry, you get the inner product of the residuals of a regression of x1 on all other variables. M is the residual maker matrix. Well, we actually have m times m, but that is just equal to m. So we get x1 times m, which creates residuals for a residual regression of x1 on all the others, times m times x1, which again creates the same residuals. And in the second entry, what we get here is actually something which is going to be, well, in this case, exactly equal to 0, but it's going to be, for us, very close to 0. So the first entry in this vector here is going to be this inner product of residuals, and all the other entries are going to be 0 or close to 0. Well, and that same thing we can do to any of the other rows. And as you can imagine, if you get other rows in the jth row, it will not be the first entry which will give you this, but it will be the jth entry which will give you that. So the jth diagonal element is then equal to this inner product, which of these residuals, which of course we can also write differently, right? Take the regression, just directly take the residuals from xj on x minus j. And well, this thing, of course, is also then again related to what we are actually solving for, because this is part of the Lasso objective function, and we actually minimize this plus the Lasso penalty. And so now what they are suggesting is, well, take your matrix here that you got from all these what we call node-wise regressions, one variable on f x on all the others, and then multiply that with the diagonal matrix, where the diagonal is actually the value of your Lasso objective function. And this value, of course, is to counteract this effect here. Note that we take it to the power -2, right? We get something. This here we want to divide by that to get something close to 1, because we want to end up with an identity matrix, or at least approximately an identity matrix. So this takes care of the diagonal, right? Multiplying, actually dividing by this matrix, by the elements here on the diagonal in this matrix. And this matrix gamma takes care of the off-diagonal elements. So it's killing the correlations between these variables. And this is again a Frisch-Wauck kind of argument, right? We're doing regression of 1 on all the others. And we know that that residual of that regression is of course going to be uncorrelated with all the other variables. And that's exactly what is happening here, right? There's correlation here. We decorrelate here by taking residuals, and then therefore we kill all these non-zero entries of the diagonal. And in fact, we can even go one step further and rewrite the process like that and say, well, we could do a regression with the lasso of y on all the other variables, as well as of xj on all the other variables, and then write the Desparsified Lasso coefficient of entry j as the Frisch-Wauck kind of regression of the residuals of these two regressions minus a bias correction. And this bias correction, because we do that, we also call the Desparsified Lasso actually the debiased lasso. So we can also interpret, if I go back, we can also interpret this thing that we add here as a bias correction, which is why it's also called often, for instance, in the book in SLS, this is called the debiased lasso, this method. Now the nice thing about the Desparsified Lasso is that it actually gives you the joint distribution of your estimate of the whole vector. So it's much more easy to do tests on groups of parameters, unlike the post-double selection method. Still, we run into problems if you would have too many parameters. So for instance, you might think, okay, I can do impulse response analysis. Well, actually, that is very unclear if that is possible. The reason is that if you do these tests on these large number of variables, central limit theorems and so on do not hold anymore. Now, again, as I mentioned before, if we can express our hypotheses as statements about the maximum of parameters, and that can be the maximum of many or even all parameters, that is something actually that you can use indeed this distribution that you get. So there are results which show that that is actually still allowable. Now, this of course is very nice, and it means that it's a very nice, quite general method that you can use to do inference on lasso coefficients. Now, of course, for the lasso, this one is particularly for the lasso, so you cannot slap this on any generic model selection method, unless you actually would consider that it actually indeed works and it does do the job. So you could do it, but you would need to be more careful there. Now, another thing, of course, that we have here is that model selection is lost. So if you really want to interpret which variables are more important and which ones are not, well, then of course this method is probably not the way to go. And we also need a bit stronger conditions on the DGP to ensure validity, and that mostly has to do with the fact that we need this kind of result here, and so we need to be more careful about eigenvalues of these covariances and so on. in fact, you would need the same conditions if you would do post-double selection, but on all coefficients. And it also means that, in fact, if you're only interested in, like, say, the post-double selection setup, where you have one variable, which is your treatment variable, then actually the method becomes much simpler, because you don't need to do this whole matrix, which is slow, because you need to do all these Lasso regressions, but you only need to do those rows. Let me go back here. Those rows which actually matter for the coefficients you're interested in. So if you're interested only in the first coefficient, you only need to do the regression of x1 on all the other variables, and you don't need to do all of these. Now, of course, that must mean that it's implemented in a package if you want to use it. So the standard package is not implemented. They always calculate the whole thing, and that makes it quite slow. But on Canvas, you'll see a suggestion for an alternative package, which is in R, which is a lot faster, because it does allow you to only do this for a subset of rows. And in fact, it also allows you to do this for time series models. Now let's have another look at how this works in simulations. Now what I'm going to do is very similar to before. So I'm going to again take a regression model with 10 variables. First beta is 2, beta 3 and higher are all 0, and beta 2 varies between 0 and 2. Now I'm not doing inference now on beta 1. I could do that, of course, also. But I'm going to do inference now on beta 2, just to try something else. And we also saw that actually this was also very problematic if we did inference on a coefficient which was selected and which could go close to 0, because it could just get kicked out. Well, you would say with certainty that it would be 0 if you do the regular Lasso. And that's why we got these really horrible coverage probabilities here. Because essentially here we ended up with cases where we did not have an interval. We just had only the point 0. We say, okay, our variable is not selected. We say with certainty it's equal to 0. Now let's see how the Desparsified Lasso corrects that problem completely. So it does a really good job. Even if beta is actually 0 or very close to 0, you don't have any problems with our method. Then you see that it does in fact not depend here on the value of beta. Now if we make the problem a bit harder, so I'm going to increase the correlation a bit, then you see that of course it's not as perfect as it seemed in the previous graph, but still it does quite a good job, and it's better than least squares, which is here. And yeah, well, I mean, this is what the standard methods do, right? So this is clearly much worse than what the Desparsified Lasso does. Well, again, let's look at a bit more variables. It becomes even more horrible for the other methods here. The Desparsified Lasso still continues to perform quite well, and even a bit better because we have a larger sample size. So the asymptotic normality kicks in a bit more here. Now, it's not a perfect method. As you can see, if we only had x1 and x2 be correlated, then it does suffer a bit. But still, at least it suffers uniformly. So this is something we could correct, right? We could do some sort of finite sample correction, or maybe do a bootstrap. This is something you can correct. This dependence on beta is something you cannot correct. That is going to be the problem for all the other methods. So, well, even in this case, I would still say it does what it should, right? It does create this uniformity, the non-dependence on the value of beta anymore. So this is another method that we can use. Sometimes there are situations where you can use both post-double selection and the Desparsified Lasso. There are other settings where really one of the two is the way to go. Either way, we now have quite some tools in our toolbox to do proper high-dimensional inference